Hi everyone. Alright, I'm going to try to walk you through a few of these solving quadratics by the square root method problems. So starting off from where you've seen it before, probably in geometry, maybe 8th grade, with the Pythagorean theorem, you have solved problems before that have a squared term. So for example, this one up here, a Pythagorean theorem problem, you know you have a squared plus b squared equals c squared. And a problem like this would be solved by plugging in for A, B, or C and solving for the missing piece. So just to walk you through one, this one on the left, A and B are 3 and 4. So we have 3 squared equals, 3 squared plus, rather. 3 squared plus 4 squared equals x squared. And you do your normal simplifying, combining like terms. In this case, 3 squared is 9, 4 squared is 16, and you get 25 equals x squared. Now at this point, you might have either been solving this just by sort of rote typing it into your calculator or knowing you're taking the square root without actually thinking about the step you're doing, which is doing the inverse operation here. You're unsquaring. You're taking the square root. And the reason you're doing that is it gets you x by itself. The same reason with a normal equation that you divide by the number in front after you've added or subtracted any other terms away in order to solve for the number. And you got, let's see, in this case, x equals 5. And you could have done the same thing with this other equation on the other side, similarly, but plugging in for A or B and C instead. So really quickly, 5 squared plus x squared equals 13 squared. Again, combining your like terms or simplifying, we have 25 plus x squared equals 169. Again, following your normal equation solving steps, we subtract 25 from both sides, get x squared equals 144. And again, inverse operation, we're using the square root to get x by itself. That's how you undo an exponent, is you take the root of that exponent. That's what gets rid of it. And you're left with x equals 12. Now, what the Pythagorean theorem was sort of hiding from you is that if you actually look at this equation and see that it's x squared equals 49, you're seeing what number times itself equals 49. And yes, the square root of 49 is one of those answers. But if we think about it, so is the negative square root. So in fact, when we're solving this, when we're using an inverse operation, it's not actually just the square root, which always returns a positive number. It's the positive and negative square root. So you get, at the step that you're taking the square root, you're getting a positive solution and you're getting a negative solution at that step. So let's walk through some of these problems. So here we have exponents around the thing that's being squared. We still want to do the same thing though. The only inverse operation we can do at this point, because we're solving an equation, we're looking to get x by itself, the only thing we can do is to take the square root. And again, like any equation, we have to do the same thing to both sides. But like I said, at this step, we're taking the square root. That's not really the only possible solution. We really, the true inverse is the positive and negative square root, because there's really two different options here. There's two numbers that you can square that will get you 16. So left on the other side, the exponent's now going to be gone. That's what the square root does. It's the inverse. It gets rid of it. And over here on the other side, I'm going to positive and negative the square root of 16, which is 4. Now, what I'm often going to do is at this point write it as two separate equations. Give one that's x minus 4 equals positive 4, and the other is x minus 4, still the left-hand side, equals negative 4. I could actually have left it there, the positive and negative sign, and solved it through that way, but usually at this step it's going to be easier to split it up. And then we just have two simple equations to solve. On the left-hand side, I'm just going to add 4 to both sides to get x equals 8. And on the right-hand side, same thing, I'm adding 4 and getting x equals 0. And those answers, 8 and 0, those are my two solutions to this original equation. At this step, if I wanted to, you could see that plugging in either of those numbers and simplifying, you'd get a true equation. So 8, for example, if we were to plug that in up here, we would get 8 minus 4, which is 4, squared equals 16. Same deal, 0 minus 4 is negative 4, and negative 4 squared is 16. Both of those are the numbers that would work for that equation. All right, we're going to go with a few more relatively difficult ones, but they're still following the same steps. So you're still solving an equation. You're still using the same steps you would for an equation that didn't have exponents in it, up to the point that we need our new step, right? So we still have the same, basic set of rules, that involve parentheses, exponents, multiplication and division, addition and subtraction. We're just adding in the fact that exponents are really accompanied by roots, or that they're really the same thing. All right, so here in this equation, we're going to start off by adding 13 away. It's the one operation we can do that's not going to have any effect on this whole set over here, the 2x plus 2. It's just going to be able to leave that alone, but it is going to be able to get rid of the 13. One of the reasons I wrote the order of operations is, generally speaking, with most equations that we're going to work with, you can usually start at the bottom of the order of operations, adding and subtracting, do that step first, and work your way back up. So we want to get rid of adding and subtracting. We've done that. We now have 2 times x plus 2 squared equals 50. At this point, again, you really couldn't distribute even if you wanted to, even if it was the right move here. It's not allowed. This isn't just x plus 2, it's x plus 2 times x plus 2. So in order to get rid of it, we're going to do our next step in line, multiplication division. We're going to get rid of this coefficient, just like if this whole x plus 2 all squared, if that were just one exponent, we'd do the same thing. So we're going to divide both sides by 2 and get x plus 2 all squared equals 25. And now we're at the square root step. We want to get rid of that whole thing squared, and so we're going to take the positive and negative square root and get x plus 2 equals plus or minus the square root of 25, which is 5. And then these are relatively straightforward equations to solve. Subtract 2 from either one and get x equals 3 and x equals negative 7. And again, those are your two solutions. I'm going to do one last one. This is about the weirdest we're going to run into, because we're not going to run into negative square roots. So I'm just going to walk right through this until we get to the tricky part. So we're going to subtract 14 from both sides, get negative 2, 3x minus 7 all squared equals negative 12. Divide both sides by negative 2, and we're left with 3x minus 7 all squared on the left, and negative 12 divided by negative 2 is positive 6 on the right. All right, we're left with now just this whole item squared, so that is why at this step we want to take the square root. We've also already run through our adding, subtracting, multiplying, and dividing, so we're up to the exponent step. And again, it's really the positive or negative square root. So we're left alone 3x minus 7 equals positive or negative the square root of 6. And the square root of 6 is an irrational number. It's not going to come out evenly. In fact, it won't even simplify. So we're really just going to leave it all by itself. Not going to turn it into a decimal. I'm just going to leave it there. And we can still turn this into two equations. We have equal to the square root of 6 on one end and equal to negative the square root of 6 on the other end. And at this point, these are just two-step equations. The key is that you're really not, again, you need to leave the square root of 6 an irrational number. Almost treat it like it's a variable. It's just a piece that you can't really combine with the other numbers very easily. So we're going to still add 7 to both sides, and we're effectively just moving that 7 over, and it's becoming positive. So it's now 7 plus the square root of 6. And over here, 3x is 7 minus the square root of 6. Again, we've just added 7 to both sides. And the same thing, like you would with any equation, you're dividing by this 3. And we have two options here. One, when we're dividing by 3, we could just write it all divided by 3. And that's technically accurate. You could also think of this divide by 3 as sort of distributing through, so you're left with 7 thirds plus the square root of 6 thirds. And here, 7 thirds minus the square root of 6 thirds. Now sometimes there's a reason for that, like for example, if this had been 6 thirds, for example, or 9 thirds, that's something that would simplify on one side but not necessarily on the other. So that might give you a easier to look at solution. Otherwise though, this is fine the way it is, and it also would have been a perfectly fine final answer to look like that and that as well.